Okay, here's a video response for driving car answers on their rotary valve issue. Okay, this is from 2019. I playing around with this thing, making a supercritical engine, SCO2. Okay, you heat SCO2, it makes pressure, yada yada yada. That's what the cool turbine guys are doing right now. Anyway, I wanted to make a piston design based on that. Mind you, one that I could also build in my garage. So the first design used a piston and bash valves. You know what bash valves are. The piston comes up, the pressure is back here, okay? Super crude, mind you. You're not going to get anything that technical here. But these are all old drawings. But yeah, anyway, the pressure would be back in this line, which would hold down the valve, okay? Just all that pressure. Where is it? Oh, where's my thing? Somewhere on here. I have how many bar it is. It's so many bar. It's high pressure. Like, I think it was like 6,000 or 8,000 psi. There it is, 7,000 psi. So yeah, I got 7,000 psi holding this down. When the piston comes up, it's going to hit that valve and force it up, and air comes in. That was the first design, bash valves. Obviously, there's a problem with bashing valves. Eventually, they pancake, and you have an issue there. So, what do? We get rid of valves altogether. Second design, get rid of that. I have this, your little Subaru sliding piston engine. Okay, what I got going on here is I have this one. Here we are. You have a piston and a chamber, pressurized chamber, and that pressurized chamber pushes the piston a direction. Okay? Right here you have a bearing. Okay? You just have, what is this? That's just a guide bearing. Oh no, that's a seal. That's what that is. Take it back. This is years ago, folks. That was just a rolling seal, a piece of rubber, as it can say. Okay, seal, seal, seal. Okay, light pressure seal, heavy pressure seal. Okay, by the time it gets to there, the pressure should be gone. And as you'll see, there's not much pressure to be leaked anyway. And then in here you have oil, bearing, 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 oil bearing, mind you. Oil port for oil to sit. Seal, outer seal, just a simple outer seal, maybe a seal here too. And then you have this right here, okay? So as the piston is moving, force this way, this is shoved right there, okay? And as you see, that's a center line. And as you go this way, obviously my angle's off here, but whatever, it's just for, I had to play with that later. But this is all in oil, just an oil bath. And as you can see, I got bolts holding it together. Nice and simple, hydraulic design. Everything's bolts together, everything's serviceable. I wanted to make these all machined parts so that you could sandwich them together. Okay, simple. Okay, but the problem with that was, as I found out later, here's your rough design. This piston, here you go. And here you go. Here's the super rough design. Here's your piston. Here's the actual pistons. Piston row, center line. This is where the valve is. This is where the crankshaft is. No, all right? And then you have this down here. I'm not going to show you the valve, but the valve is basically a cam bathed in oil. This hits a cam bathed in oil, and it turns it. And then that basically just turns the valve and opens it. And that way you have an ejection pulse. The problem with all these cylinders is you're wasting a lot. So doing that and figuring it was wasted, I made this cylinder super small. Where is it? 1.1 inches. I don't know how many millimeters it is off the top of my head. But there you go. And a 2-inch thing. So this is 2 inches. Okay, right here, 2 inches. 2 inch, I forget what the wall is, you can pause it. But yeah, the issue was volume. Even injecting these, okay, because if you injected it here, it's got to go all that way and you're wasting all this volume. And as it comes back, you have, yeah, so you're wasting all that volume. It's been years since I played with this. But, so what I did was I came up with this. And what you have is, you have 8 of them firing at once. And what you have is, they're not actually firing when they hit the bottom, obviously, because there's nowhere for it to go. You know, there's nowhere for the piston to go. So what you have is you have them firing right after. Okay? So it's as soon as it gets past this point, the center point here, see this is offset. As soon as you get after that center point, it's going to push, and that's going to force the piston this way. And that happens every, I don't even know how many degrees it was, but it's 28 cylinders, so you can figure it out. 8 cylinders firing at once, 28 total cylinders, okay? And once again, the volume killed it. Just the volume killed it. I just wasn't able, there's no way to heat up this supercritical CO2 easily enough. And this is a closed system, so the more pressure you have on one side, you're going to lose that pressure, okay? Yeah, so it was just the volume wasn't working out, and it's massively complex to machine all these pieces. It could be done. It could be done on a lathe, but it was massively complex, and it was a big engine. I think it came out to be 30 inches by, it was like, the block, I think it was like 36 inches wide by like, oh, I want to say it was like 12 or 15 inches tall. It was something crazy. By the time you put these cams in here, because you have 2 cams on the outside. You have 2 cams here and here, and a central cam. So the 2 cams turn the central cam, which turns the drive shaft and all that. So yeah, there you go. It was just a massive engine. So yeah, based on the volume, based on the sheer size, based on the complexity to build it, that one went out the window. So, still using the rotary design, okay? I have decided, which I'm not going to show it to you, but it's basically what you have there. It's just cam-based driven. The cam turns the rotary. The rotary doesn't have to fully seal, and the reason is here. When you open up the throttle, it's going to, the rotaries always open up a little bit. So that's going to turn the rotary, which sends pressure into the engine, which sends force to the camshaft, which turns the rotary, which injects, which then pauses, which injects, which then pauses, which injects, which then pauses. Okay, between the throttle lever and the rotary valve injecting, I should be able to pulse that enough. Okay, so here we go, your simple turbines. Okay, and it's a think of a rotary engine, best way I could put it. You have your 3 stages, okay? First stage, second stage, third stage. You can see how I got it all technical with the heat here and how much heat you're going to lose from here to here to here. By the time it gets to this third stage, these are all set. It's actually something like this. Here you go. So there you go. Once again, low profile, Subaru style, you know, boxer style engine where it's nice and low in the chassis and wide. And I can play around with however you do it. You can make a triangle, you can do whatever. You can make it fit in almost anything as long as you have 3 circles. Okay? Doom, doom, doom. By the time it gets here, it should be cool. And that's important because your CO2, oh, where is it? I forget the temperature. The hotter you have on one end versus cold on the other end, the bigger pressure differential, the more power you can make. Simple as that. So yeah. So yeah, 3 things. It's what I've gone with. I'm playing around with it. Give me time. I have so much life stuff going on. But yeah, the rotary valve is still in play here. These still turn a camshaft, which turns a rotary valve, which acts as an injector for a pressurized system. It's all pressurized. There is no spark. There is no feel. There's some fuel to heat up. Okay, but that's what I'm going off of. And the thing is with supercritical CO2, there are many ways to heat it. Okay, you can use electric if you want. You can use kerosene. You can use gasoline. You can use whatever you want that makes the heated chamber, which I don't know, I have it around here somewhere. The heated chamber hot. Hot enough to make supercritical CO2, in which that temperature, which that has to happen to make a couple bars with pressure, is not high. So yeah, playing around with it. But yeah, as far as rotary valves go, it was a failed design just based on the volume. And rotary valves are nice, but as you've remarked, they have lots of issues. And the key to a rotary valve is not having it touch a burnt surface, because all that super hot heat hurts things. So if you can eliminate the super hot heat, keep it back here, inject it, cool, whatever, it works. So yeah, these are becoming a pain to make, and I'm looking for alternatives. I've been looking for alternatives, but actually making these turbine blades stand up to several hundred degrees on a constant basis, oh yeah, we're moving them a lot more RPM, obviously, than this thing. This thing was this was a torquing engine, okay? Super torquer. This sucker's an RPM engine, obviously. Massive RPM, geared down. No gear reduction, well, minimum gear reduction, because you have 2 and then you have 3. Where is it? You have 2 gears here, and you have a big gear here. So yeah, a little bit of gear reduction in it. But once again, that's my failed design. Discussing rotary valves. But the rotary valve thing was just a failure because of the sheer volume that it lets escape. Okay? And if you have a system like this, you can limit that loss. Okay? If you have a little bit of excess on a high revving engine, it's not a huge deal, okay? It's not a huge deal. Versus if you have a little bit of excess on a low revving engine, you're filling that chamber more than you need to, which is wasting. It's just wasting it. So, yeah, not wasted. But yeah, there's my take on rotary. Just a little thing for you. It ended up way too long, unedited video and all that. So yeah, there you go. Fun. Thank you.